Hello students, welcome back to the Tantray physics classes, and today we are discussing one more problem set on rotational dynamics. So the first problem that I want to explain, it is a disk and its moment of inertia is 200 kg meter square and its initial angular velocity is 0. We apply a torque on this. By applying a force, then that force produces torque on this. Maybe there's a tangential force and there is arc here. Arc F is the torque, and this torque is applied on the disk about the center of mass. Question is, find the angular velocity after 3 seconds. That's all. So what to do here? We know certain formulas of rotational dynamics. Like you see, torque is equal to I alpha. This is one formula. Torque is equal to R cross F. This is also the formula. Torque is also equal to R F perpendicular component of force on the radius vector, or F R perpendicular. This also. Well, these are our formulations for torque. And also we know, you see, final angular velocity is initial angular velocity plus alpha into time. This also we know. So we will find answer. We will try to use any of these formulas. So which formula I am going to use? First one and the last one about this torque. Right? So we know torque is equal to I alpha. Now torque is given to be 1000 is equal to I, that is 200 into alpha. What is alpha? That is 1000 by 200. It is 5 radians per second square. This is alpha, angular acceleration. When there is angular acceleration, certainly the angular velocity has to change. It will be increasing with time. So what is the final angular velocity? That is initial angular velocity plus alpha t. Final angular velocity is initial angular velocity. If I suppose that initially the disk was at rest, there was no rotation of the disk initially. So omega 0 is 0 plus alpha is 5 and time is 3. So omega is what you call as 15 radians per second. That's all. So we got the answer to this problem. At this initial rotation 0, but you apply a torque and its rotation will increase. There will be alpha angular acceleration, and we want to find what is the final angular velocity after some time. So we have used this formula and this one, and we got the answer. So the second one. This is the second problem. The problem is this: a wheel. This is a wheel, and it is rotating with frequency. Is not angular frequency, it is just frequency, 720 revolutions per minute. Its moment of inertia is given to be 24 by pi kg meter square. It is already rotating with frequency 720 revolutions per minute. In 1 minute it makes 720 revolutions. We are applying a retarding torque. Retarding torque means which will decrease its angular frequency, or which will decrease its frequency. So we are using opposite torque, means the force is in this direction and that will create a torque, and that torque we have to find. The wheel is brought into rest in 8 seconds. When we apply a torque, the wheel was rotating and it retards down and finally it stops after 8 seconds. We have to find how much is the retarding torque. The wheel is brought to rest in 8 seconds, find the retarding torque. We have to find this torque. So what to do? First of all, this F, this frequency, I will convert into omega, revolutions per minute. That is 720 by 60 revolutions per second. Right? It is 12 revolutions per second. This is F. What is omega? Initial omega. Initially it was rotating with this angular frequency, that is 2 pi f. That is 2 pi f means 24. It is radians per second. Now initially the wheel was rotating with omega 0, that is 2 into, no, it is 2 pi f 12, 2 pi into 12 radians per second. We are applying a torque, and now this wheel will retard down, and finally it will stop in 8 seconds. We have to find how much torque we have applied to bring it to the rest in 8 seconds. That's our question. So we'll use this formula. Omega is equal to omega 0 plus alpha into t. What is this omega, final omega? Finally, it is at rest. I mean, it has been retarded to get the final angular velocity to 0. So it is 0. Initial angular velocity is 24 pi plus alpha, that is torque by moment of inertia. That's what we know. It t in 8 seconds. So what is this torque? This torque is equal to 24 will get to the left side, multiply this I, divide by 8. That is 24 pi by 8 into, how much is I? That is 24 by pi. Pi gets cancelled. Pi gets cancelled. It is 3. It is 72 Newton meter. That's the torque. So 72 Newton meter torque you had to apply to the wheel, so that it comes to the rest in 8 seconds. It was already rotating with angular velocity. You applied reverse torque, and it retards and finally stops in 8 seconds. 72 Newton meter torque you had to apply to bring it to the rest in 8 seconds. Third one. This one is the third problem. This sphere which rotates about its center of mass axis with 600 radians per second. To keep it rotating with this omega, otherwise due to friction, maybe it is rotating in space or in some frictional environment, it will retard down and will become finally to stop. But to keep the angular velocity 600 radians per second constant, we have to maintain its angular velocity. For that, we have to power it. We have to apply power to the sphere, and the power is 1.2 kilowatt. Power is 1.2 kilowatt. So here is a sphere which we need to rotate at 600 radians per second. But for this, we have to supply power to it. We have to rotate it continuously. Otherwise, it will stop. The question is, you power it by 1.2 kilowatt. How much torque is needed to supply this much of power to keep it rotating with omega is equal to 600 radians per second? That's our question. How much torque you have to apply to this sphere to keep it rotating with 600 radians per second? And that torque will supply a power of 1.2 kilowatt. So first of all, let me go to some basics. How much is work done in rotating a body through an angle of theta? Let me suppose. How much work is done? Let me find it out. Work done in rotating a body through an angle of theta. If you turn a body through an angle of theta by applying torque, how much work has been done? So small work done is torque d theta. Torque into angle. Torque applied into angle that turns the system by d theta is the small work done. If you integrate this, you get the total work done. Tau d theta from theta 1 to theta 2. This is the work done. This is the work done when the applied torque rotates a body through an angle of theta. However, if torque is constant, then W is equal to tau into delta theta. Torque, constant torque into angle through which the body rotates. If you multiply them, that will give the total work. That can be done from here. If torque is constant, torque will come out and you have to integrate d theta. That is this. But if you differentiate it, I mean, the work done by delta t is equal to tau delta theta by delta t. That will make it power. Work done per unit time is power. So power is equal to tau, what's d theta by delta theta by delta t, that is omega. So we have a relationship between power, torque, and omega, angular frequency. That is, power is equal to tau omega. That is our now equation that I have developed through here. So basically work done, that is torque into angle, power work done by time, that is torque d theta by time, that is torque into omega. So this is the base equation. It is the corresponding equation in translational mechanics as power is equal to Fv, force into velocity, in translational mechanics. Anyway, let me go to the problem now. Let me solve the problem now for you. Now see here, power is equal to tau omega. Now power is given to be 1.2 kilowatt watts. Torque we have to find, and omega is 600. What is torque? Torque is equal to 1.2 into 10 raised to power 3 by 600. Torque is equal to, it is 2. Point will finish, it will go 0, this will cancel, 2 Newton meter. That is the torque that you need to provide a power of 1.2 kilowatt to rotate it with an angular frequency of 600 radians per second. So a body, to maintain this rotation at 600 radians per second, we need to apply power from outside, and that power is 1.2 kilowatt. But for that power, we need to apply first torque. That torque will produce the power. So how much torque we have to apply to this sphere to maintain the angular velocity of the body at 600 radians per second? Okay, now the fourth one. Yes, this is fourth problem. The problem is like this. This is a rod which can rotate about this hinge. It is a hinge. It can rotate like this, up and down. It can rotate like this. And on this rod, which can rotate about this hinge, okay, let me call this hinge point O. It is center of mass C. Two forces act. First of all, it is gravitational force acts downwards. And second, you are applying upward force mg by 2, half of this gravitational force, right? And we have to find what is this angular acceleration about this hinge. It rotates like this, like this, like this. What is the angular acceleration of this rod about this point O? That is our question. So first of all, I have to find torque. What's torque? How much torque this mg is creating? It will create anti-clockwise torque, anti-clockwise. That is mg into shortest distance from here to here. That is L by 2. And this is force R cross F. This is anti-clockwise. This is anti-clockwise. No, R cross F. Oh, sorry, R cross F. It is clockwise, and this is anti-clockwise. This force will create anti-clockwise torque. This creates clockwise torque because R cross F. R is to be crossed into F. So it is minus, therefore, mg by 2 into distance from here, shortest distance on this force line, that is 5L by 6. That is, LCM is 12, right? It is 6 mgl minus 5 mgl, right? Okay, then torque is mgl by 12. We got the torque, and we will put this torque equal to I alpha, right? Now what is alpha? Alpha is equal to this mgl by 12, this one, divided by I. So alpha is equal to mgl by 12. What is I? Moment of inertia of this whole rod about this. It is an axis passing through one of the ends. So it is 1 by 3 ml square. 1l gets cancelled, m gets cancelled. This is 4. Alpha is equal to this g. It is 4 into L. This is the answer for the question, fourth one. So the problem was like this: a rod which is movable about the hinge, and two forces act on the rod. First it is weight, and then applied external force mg by 2 upwards. This will create anti-clockwise. This will create clockwise torque, and this will create anti-clockwise torque. So we find net torque mg L by 2, mg this L by 2, mg by 2, that is this force, into L by 2, and we get torque mgl by 12 is equal to I alpha, and there we get alpha here, G by 4L, right? And this is the fourth one, fourth problem on rotational dynamics, and I will continue solving problem on rotational dynamics. You just watch the lectures. Thank you.